This is really the ideal case analysis where we assume that everybody has unlimited cache space, everybody's participating in the network, and whenever somebody meets somebody else in the network, all of their data that the person has previously downloaded gets transferred, and likewise that works both ways, so it's reciprocated. So they essentially share all packets that they've ever downloaded with each other. So just to sort of visualize that, if you picture the green man here as being the one with the data, travels into this network of people and infects these people with the data. Again, infection, not the best choice of word, but it sort of describes what's going on. Now if this person was to move to another network, likewise it infects these people with the data. So the second research question is where we say, okay, well, a little bit less of an ideal world. Now we're going to place some restrictions on the actual cache size of these devices. So how well does it work when we start to place restrictions on how much space these devices have available to actually store this stuff? Now, what sort of distribution we ultimately end up using for this hasn't been decided yet. In practice, we'll probably try a few, so we might start with something simple like a uniform distribution where all the nodes in the network have exactly the same amount of storage, and then we try different distributions and see how it changes things. Again, just to visualize this, so this is a case where we don't have unlimited cache space. So the green data man moves across here, infects all these other people with the green data. Then when the pink data person moves across, some of these green data people actually have to throw out their green data in order to make room for the pink data. Some of the people get to keep both the green and the pink data I've shown here, but this is just to sort of illustrate that there's not necessarily unlimited cache space. So the third research question is this. Now we're saying, okay, well, let's constrain it in another dimension. Let's not look at cache space anymore. Let's actually look at it in terms of the rate of device participation in the network. So we're saying, how does it affect things if not all devices are participating and sharing data in the network? So again, to visualize, this is now the situation. Notice that not everybody gets a copy of the green data anymore. So these are the people that aren't participating, the blue people now. Now notice, of course, if one of these blue people moves over to this other network, then the blue person doesn't have any data to share, so nothing gets shared. If one of the green people moves over, then it gets shared with some of these people, but again, because we don't have perfect participation, not everybody is getting a copy of the data. So again, for this, we haven't decided at this point precisely what distributions we'll use in terms of figuring out who is and who is not participating in the network. But ultimately we'll probably trial quite a number of these and see how things change. So as a concretion now of how can we actually start testing this on real data? Well, at least for my PhD, we're looking at actually doing this on the James Cook University Walkabout Wireless Network trace. So what we essentially have is a trace of all the packets that are flying out to devices connecting to the JCU Walkabout Wireless Network, which is just the wireless network on the JCU campus. And essentially what we do with our analysis is to say, okay, the first thing we need to know is when devices are in encounter range of one another, or when devices are in transmission range, and we call this encounters. So because we don't have instrumented devices, we can't do a perfect job of this, but what we can do is sort of approximate it by saying, okay, well, anytime we see two devices that are attached to the same access point simultaneously, we're going to assume that those two devices are in transmission range or have encountered one another. So with that knowledge, what we can now do is say, okay, we know when devices encounter one another, and we know which packets devices are getting from the network and so have in their caches. So based on this information, we can simulate the possible or potential transfers of these packets between various devices. And we can do this by looking for common bit strings in the data. So we'll have to do some kind of filtering of this data to actually remove generic packet headers and the likes and actually pick out what is the actual data in this. But basically we'll come up with some kind of reasonable demarcation of what a packet is of data after we've gotten rid of all the headers and other irrelevant pieces. And then we'll look for common bit strings in this data to actually match up the things that people are requesting that are common between multiple people. Now, so if we can figure out in the network, okay, that somebody has downloaded some piece of data, they've shared it with somebody else, and what's happening at the moment is that that person they've shared it with is currently getting it from the infrastructure at a later time, then we can then earmark that packet as being one that they could have theoretically got through this internet-based madnet rather than needing to rely on the infrastructure. So just a bit of an idea of the scale of the data. So between the James Cook University, Townsville and Cairns campuses, the Wi-Fi network operates at a peak of about 300 to 400 megabits per second. So if we were to do sort of a current day worst case analysis, we'd be looking at about 4 terabytes of raw uncompressed data for a day. Now, in practice, I think what we'll find is that the average bandwidth is probably going to be somewhere around 100 megabits per second. So more realistically, we're probably looking at about a terabyte of data for any given day. And of course, this is actually in its uncompressed and unfiltered form. And what I think we'll find is that once we actually get into the processing of this data, we'll be able to actually reduce it down quite a bit. So this is sort of a medium-sized data set, and it will require, some of this. There's going to have to be some kind of algorithms. We'll have to further investigate what our options are for actually processing this data on an algorithmic level. In terms of machinery and hardware, well, there'll probably be a little bit of this. I'm not sure exactly what HPC or high performance computing infrastructure this picture is, but we'll be using the James Cook University high performance computing infrastructure. I don't have a picture of that. In fact, I don't even know what building it's in. I know how to access it though, so that's important. But yes, I'm not sure where it's physically located or whether it looks anything like this or bears any resemblance. The other option also is actually this, which is to say there's a lot of labs on James Cook University that spend most of their day actually unoccupied during the night and during the early morning. So I've got some ideas there, and this is really a topic for a completely different talk of how we might actually be able to do some neat tricks just using the web browsers of these machines, so not even have to modify the software stack on these machines to actually do some of this data processing. So we'll probably be looking to employ some kind of MapReduce paradigm essentially around this data processing. So we could, for example, do a distributed count of packets and essentially look for the common packets and all device names or device identifiers that have requested some given bit sequence, and that sort of thing. So I just want to give now a little bit of a critique of the data set I've chosen, because it's not perfect. Most data sets aren't. But I've given a subjective rating to a couple of different properties of this data set or features of the data set, and I'd like to hear at the end also what I'll actually do in the non-internet version. It's not very useful here, but feel free to leave comments if this is posted somewhere where comments are accepted. What you think about the data as well. So the first thing I want to discuss is external validity, or how well does this data set actually generalize out to the greater world. So if we come to some conclusions based on our measurements within James Cook University, how well is that going to generalize out to other data sets or the world at large? And I've only given this a C on a grade scale of A to an E, because I think we need to be very careful about how much we generalize out of whatever results come out of this. It's really only a single experiment conducted in a single university environment, and ultimately what we want to be able to do is to actually build up a portfolio of different data sets to be able to say, okay, well, it works in this sort of way in this environment, and then when we look at another environment, it's either the same kind of things or it's different in some respects. So ultimately we want to be able to compare and contrast how it works in different environments. But in terms of drawing sort of premature conclusions from the James Cook University data set, we need to be very careful about how far we go in saying this is either good or bad simply based on this data set. So duration. The duration is very hard to gauge in terms of whether we're collecting a good samples or good duration of data or not. The reason for this is that we're not completely sure how much data we'll be able to collect. I think in the uncompressed form it's certainly feasible that we'll be able to get at least a few days worth of data. By the time we've actually done some processing on it, I think we could probably even get it up to potentially months of data, maybe even longer. The other thing that makes it hard to gauge how well or how good the duration of our data collection is that it's not sure until we actually do the analysis how much data we're going to need before we start to see any kind of trends or patterns emerge in the data. So for the time being, I've given it a B, but that's sort of subject to change based on our analysis really in collection. So sample size, excuse me. So sample size it's not too bad. The James Cook network had about 14,000 devices or wireless devices running over it in the first 6 months of 2011. I think it peaks at about 400 plus simultaneous devices. So the sample size isn't too bad. It's fairly good actually compared to a lot of research data sets. You'll often find with research data sets with these kind of experiments, they're often quite contrived, and the number of devices is, say, in the range of tens of devices, and they've all been given out to people in a single building, or they're all given out to research students, for example. So I think our sample size is actually fairly decent, but in saying that, it's not tens of thousands or hundreds of thousands of devices, and we can't practically, at least at this point, do the kind of experiments that some of the larger companies that have software installed on all these devices could potentially do. So exactness. Well, we're fairly exact in our packet trace in that we're looking to have a complete packet trace collected. Where things aren't completely exact is to do with the nodal encounters. So as I've said earlier, we're sort of approximating what a nodal encounter is, and we're saying, okay, well, wherever two nodes are simultaneously connected to the same Wi-Fi access point, we're going to assume that they're in transmission range and so have encountered. So there is some approximation there, but it's probably not going to be too bad. Completeness. So do we actually incorporate all of the data? At a first look, you would say yes. You'd say yes, you've got a complete packet trace of everything that's going across the Wi-Fi network to these devices. So we've got all the data. One thing that's interesting to consider is that we're going to actually be missing some data that people are retrieving over their cellular networks. So because we don't have the actual devices people are using instrumented, we can't actually see what they're requesting over networks other than the Wi-Fi network. So they could potentially be carrying around other useful information, but we don't actually have the instrumentation to see that. The other point to make is that, excuse me, is that also there'll be nodal encounters that we can't actually pick up, and these are going to be ones that happen during times where, for example, you've got two devices and neither of them are in range of any of the Wi-Fi access points. And they may, cross paths, so two people walking between buildings crossing paths, neither are connected to a Wi-Fi access point, but their two devices are actually in encounter range. So later on, I'll start to explain how we might be able to get a little bit more insight into encounters outside of Wi-Fi access range, and also to do with maybe increasing our exactness in things as well. So progress to date. The first thing is this: some people like to have degrees up on their wall in their office. That's fair enough. You want to show your qualifications. I'm actually currently working on something far harder than that, which is getting printing working from laptops on the James Cook University network. So you can see here I've got 3 working